The Great Pyramid of Giza is an absolute marvel of engineering that contains approximately 2.3 million individual stone blocks. Looking at the people and camels resting at the base, the sheer scale of the limestone becomes clear. Each of these lower course blocks weighs around 2.5 tons. Pharaoh Khufu ruled for roughly 20 years. That timeline established a hard physical deadline for the entire project. Divide 2.3 million blocks by the available daylight hours in 2 decades. The builders had to place one block every 2 to 3 minutes. This relentless pace is the ultimate stress test. Any viable construction method must work at this punishing speed. These numbers suggest that only a rigorous engineering audit of Bronze Age capabilities can explain the structure's existence. The first hurdle was basic transport. Dragging a 2.5-ton block on a sledge across dry sand requires a massive, impractical amount of pulling force. This diagram shows the dry sand scenario. Sand piles up in front of the runners, spiking friction. Engineers solved this by pouring water in front of the sledge. The wet sand panel reveals capillary bridges binding the sand grains together, smoothing the surface. These microscopic bridges create a smooth, stiff gliding surface. This technique slashed the required pulling force by 55%. Mastering this fluid dynamic trick allowed a team of just 50 workers to maintain the brutal block delivery schedule from the quarry. Once the stones reached the site, they had to go up. The most common theory involves a single, massive ramp built up the side of the structure. For the wide bottom third of the pyramid, up to about 43 meters in elevation, an external ramp is highly efficient and mathematically viable. Humans can only navigate an 8% gradient. To reach the apex, the ramp must continuously extend outward, eventually stretching 1.8 kilometers into the desert. Volume data shows this theoretical ramp would require significantly more material than the pyramid itself. Because the straight ramp fails the engineering stress test at high elevations, the builders changed their construction methodology mid-project. This schematic outlines the hybrid ramp system. At mid-elevations, the builders likely utilized internal spiral ramps built directly into the structure's core. But an internal ramp cannot easily handle the most extreme weight challenge, lifting the 60-ton granite ceiling beams for the king's chamber. This is the Grand Gallery. Its steep angle, smooth floor, and massive corbelled walls suggest it functioned as an industrial lifting shaft. Under the counterweight pulley theory, workers rolled 11-ton blocks down the gallery floor. Connected by ropes through a pulley system, these weights hoisted the 60-ton beams into position. Above 100 meters, where space was too tight for ramps, teams used specialized wooden levers to hoist blocks course by course, exactly as the Greek historian Herodotus recorded. The engineers achieved this by systematically shifting techniques, moving from friction reduction and external ramps to mechanical counterweights and levers exactly when required. We can calculate the pyramid's total energy budget, the absolute number of joules required to lift 6 billion kilograms of stone to its center of gravity. A human doing sustained manual labor generates about 75 watts. Spread over 20 years, the total energy required for lifting actually requires only a fraction of the total workforce. Records like the Diary of Merer show that the rest of the labor force was organized into highly specialized modular teams for quarrying, transport, and placement. This comparative analysis chart highlights the integrated multi-method approach on the far right. It shows how these verified theories combine into a single adaptive construction program. Today, the Great Pyramid stands as a triumph of human organization and the flawless optimization of simple machines.